Bismillahirrahmanirrahim and Assalamu alaikum. We've started our discussion on energy storage devices which are called capacitors. We've looked at the dynamics of how a capacitor charges and discharges. A quick recap of the discharging and charging of a capacitor. We've noticed that if we have a capacitor and we connect a battery to it, through wires, and there is also a resistor in between, which I'm representing by a thin wire. A thin wire will have a bigger resistance. Then charge is going to gradually build up on this capacitor. And if I were to plot the buildup of charge with time, I found out that if the capacitor was initially discharged, it builds up charge exponentially. Likewise, a voltage is built up across the capacitor exponentially. This is the voltage across the capacitor. This capacitor has some capacitance C. If I were to plot, instead of the charge, but the current through this circuit, this current is not going to be steady with time, it's going to change with time. Initially the current is going to be large because the slope of this line is large, and eventually the current is going to decay to zero. So if I were to plot the flow of current through this circuit, this is what the current is going to look like. And if I were to take some point inside this circuit, this were a positive plate, this were a negative plate. If I take a point P, and if I were to find out the magnitude of the electric field at point P inside the wire, that's also going to decay with time, because that is dictating what current flows through the circuit. So if I were to plot the magnitude of the electric field at point P, that's also going to decay with time, and it's going to decay exponentially. This is the electric field at point P. This electric field dictates the current. The current is being led by the electric field inside the wire. And then we came up with expressions for the voltage and the currents. The voltage, for example, across a capacitor in such a circuit is given by the charge that is built up on this circuit divided by C. And this charge that is built up on this circuit asymptotes to some value. This Vc asymptotes to a value which equals the EMF of this battery. So this Q over C asymptotes to E. That's the voltage across the capacitor when it is fully charged. And at this point the charge will cease. But the build up to this voltage is not sudden. It follows an exponential build up and is given by 1 minus E minus T over the product of R and C. So there are two time scales in this circuit. One is the time scale at which the electric field immediately establish itself in response to the fringe field of the capacitor and the field of the battery. This happens instantaneously. It really doesn't take any time, a few nanoseconds or picoseconds perhaps. And then this build-up of charge and voltage across the capacitor is on a longer time scale. So this constant RC dictates the time scale. So there are two time scales. One is the instantaneous reconfiguration of the charges and the fields, and these are real charges, by the way, on the surface of this conductor. So that's instantaneous because electric field information travels at the speed of light. And then there is a gradual build-up of charge on this capacitor and a gradual build-up of voltage across the capacitor. And the time constant is called the RC time constant. This product of R and C happens to have dimensions of time, and it just the rate at which charge is built up is governed by RC. Larger the time constant RC, the slower will be the buildup of charge. So if I were to use a bigger resistor, which means a thinner wire here, a thinner and thinner wire means a bigger resistor, or if I were to use a capacitance which is large, say large capacitors, or capacitors that are really close together, or a capacitor in which I inserted or poked in some dielectric. For such circuits, the buildup of charge is going to be slow. So RC determines the rate at which charge is being built up. So RC large, the response is slow. So for large RC, if I were to plot the buildup of charge or the voltage, it's going to be slow. It's going to asymptote at the same value, up to the same value. It's going to point in the same destination, which is the EMF of this battery, but the buildup is going to be slower. If I decrease the resistance, which means that I make this wire thicker, then the charge buildup is going to be faster. So it's going to quickly reach its asymptotic value. So this is a smaller time constant, small RC. This is a long RC, which means a sluggish response in the voltage. So this external resistor and the capacity of this capacitance determines the long time scale of the circuit. So this is how a capacitor charges. Now we've also seen how a capacitor discharges. If I were to replace this circuit with another circuit in which the battery is simply removed, then for such a circuit, it will apparently look like the following. I just have to remove this battery, sorry. There's no battery. I have a capacitor which has some charge already residing on it. That charge, let's call it Q0. Which means that if I put a voltmeter here, it's going to give me a voltage. That voltage, V0, would be given by Q0 over C. And the voltmeter must be such that it does not drain off any charge from the capacitor. So it must be a high resistance voltmeter. Ideal voltmeters really have large resistance so that they don't disturb the charge that's already on the capacitor, because the moment you connect wires and you connect a voltmeter, there is a propensity or a tendency for the charge to flow out. But you don't want that. You would like to make as unobtrusive or as non-invasive a measurement as possible. Anyways, if I have this circuit and I connect a small resistor, which is a thin wire, a resistor is just a thin wire, in series with this capacitor, this charge that has built up is going to drain off. And it's going to drain off because an electric field will be set up, which is the fringe field of this capacitor. That fringe field is going to create distribution of charges, which will make a current flow. But then eventually all of this charge is going to drain out, and we can find out how the charge drains out. We've already seen that in the previous class. If I plot versus time the drain out of the charge, it starts off at some Q0 and then exponentially drops. The voltage across this capacitor exponentially drops. This drop of the Q0 of Q is given by Q0 E minus Q over RC. Once again, it's determined by the time constant RC. And if I were to plot the current through this circuit as a function of time, that's just the derivative of this charge. That's also going to drop off exponentially. Initially the current is large because there is large amount of charge on this capacitor, which produces a large fringe field. The large fringe field causes a larger current inside the wire. But when the current is large, the drain off from this capacitor is large. So it rapidly depletes its charge. That's why the slope is large here, and then it eventually asymptotes to zero when all the charge has been drained off. And we looked at the differential equations, we solved the differential equations in the previous class, and this is something that we came up with. So this is just a brief recap. Now what I have for you is a demonstration, excuse me, in which I've actually tried to automate this process for you. So what I have is basically a capacitor, the non-drug circuit symbols, and I have a resistor in series with it. And I have two possibilities. I can either have a battery connected to this capacitor, or I can have nothing connected to this capacitor. This means that I have a switch that can toggle in two positions, A and B. So this switch can either be in position A, which means that this capacitor is seeing a battery of EMF E, and it's going to be charged. And what I expect is to fall is that the voltage on the capacitor shows this kind of behavior. It charges exponentially. But then, after some period of time, I toggle the switch, I change the position of the switch so that it goes to position B. So it can swing between A and B. And when it's in position B, the battery is out of the circuit and this capacitor would tend to discharge. So initially charge is built up on these plates because it sees a battery, and then I toggle the switch, it comes to position B, that charge leaks off. And I'm measuring the voltage across this capacitor with the help of a voltmeter, VC. And I would also like to measure the current. So placing ammeters in circuits is not really very convenient. So I would instead like to find out the voltage across this resistor, VR. This VR is just going to be proportional to the current to this resistor, because VR divided by this resistance gives me the current to the circuit. So inadvertently I'm measuring the current to the circuit through the resistance through the voltage across the resistor. However, I don't want to do this switching manually. So mechanical switching means that the switch is in position A, it swings to position B, then to A, then to B. So instead of using a mechanical switch, I replace this mechanical switch by a voltage source that goes on and off. On, off. So it's a pulsed voltage source. The on signal, which is say some 9 volts, 10 volts or 5 volts, will act like a battery, and when this is off, the current will drain through the circuit. And I'm doing all of this through a computer. So I'm creating a voltage through a computer, and I'm picking up these voltages, bringing them into a computer, digitizing the signals, and making plots of VC, VR, and the input voltage. So I've interfaced this circuit with the computer, so I can see all the voltages on a computer. But there's nothing special about the computer, it's just a sophisticated voltmeter. So this is my circuit here. This is the circuit. Alright, it's a simple RC circuit. This is a variable resistor, and here there is a capacitor. And these are just connections, these are just terminals to make connections with the computer. This is a DAC card. This is in fact a routing board that makes all of these signals, it's just like a breadboard. These signals are connected to this breadboard, the signal that goes in to a computer. And then I use LabVIEW to actually look at the signal. So here is my LabVIEW file. LabVIEW is a program which just gives a nice look and feel. It's a visual programming language that gives a nice look and feel. It helps me acquire data, it helps me generate data. So on the top window here, I can see a pulse voltage that is being created by the computer and is being fed into the circuit. Here I would like to see a voltage across the capacitor. This is a screenshot from a previous run, and this is the voltage across the resistor. Now let me run this file. Alright, so now this program is running. This is my input voltage, and this is the voltage as seen across the capacitor, and this is the voltage across the resistor. Alright, now what I'm going to do, first of all I'm going to explain this. So let me just vary the resistance a little bit. So now I'm varying the resistor, the potential, the variable resistor. This waveform is changing. Can I circuit please? Alright, now here the effects are quite evident. In the top panel we have the pulse that is being applied. It's 0 volt, roughly 8.5 volts. Here the voltage across the capacitor starts off at some 0 volt. It then rises, and it rises exponentially. It does not go all the way up to 8 volts, up to the maximum voltage that has been applied, because the pulse has now switched and it's now off. So this switch is now off, which means that the voltage across the capacitor would now tend to decrease. But then it decreases exponentially, and if you fit this line to an exponential model, you'll find that it's a really good fit. And by the time constant of this decay, you can find out what resistor and capacitor do we have inside this circuit. Now when this voltage is dropping and it reaches some point, the pulse suddenly switches. And it becomes on again, which means that the switch is now on, in the on position, in position A. This means that the voltage across the capacitor starts to rise again. And when the switch is off, it's in the position B, the voltage across the capacitor drops again. So this is a waveform of the voltage across the capacitor, which is also synchronized with the charge across the capacitor, because the voltage is just proportional to the charge. So charge is building up and it's decaying, building up, decaying, building up and decaying. And now let's look at the current. This is just the current through this circuit, because this is the voltage across the resistor. Now the current is decaying. As the voltage across the capacitor builds up, the current decays, exactly in line with what we see here. The voltage goes up, but the current goes down. And when the switching takes place to position B, the voltage across the capacitor decreases, and the current has now switched its direction. The current was positive here, and now suddenly it becomes negative. It reaches a maximum value and then it starts dropping. So during the charging and the discharging cycle, the magnitude of the current is decaying exponentially, but the directions are reversed. Can anyone give a reason of why these directions are reversed? Abu Zar? Ifra?
Firstly, the current will flow from the positive. Firstly, the current will be flowing from the positive terminal of the battery. It will make a positive, one of the plates positively charged. When it will be discharging, the current will flow from the positive charge of positively charged plates in the.
Beautiful, exactly. So in one half of the cycle, this capacitor is this plate is becoming positively charged, and it's becoming positively charged because charge is being deposited on it. So positive charge is flowing towards it. So the direction of the electric field during the charging cycle is here. However, in the discharging path, this plate that has been positively charged is now losing its charge, is shedding away its charge. This is spring for the capacitor plate, this is autumn for the capacitor plate, it's losing its charge. So as this charge loses this charge, a fringe field is set up which makes an electric field in this direction, and that causes the current to flow outwards. So the current is minus dq by dt here, the current is plus dq by dt here as far as the capacitor is concerned. So these currents and these electric fields are in opposite directions, and that's why here the current suddenly changes its direction. But nevertheless, in both the charging and the discharging cycles, the current is decaying exponentially. So I can actually increase the voltage to which this capacitor is charged by making the frequency of the pulse smaller, so that it has enough charge to go to its maximum voltage. So let's try doing that. Really? So how do I change the frequency? I would just like to, this circuit presumably still running, I would just like to decrease this frequency here. Now you see that the maximum voltage this capacitor is being charged has gone up to about 6.5 volts. I've just decreased the frequency so that the span of the pulse has become wider. I decrease this frequency even further. Right, so it's gone even further. You see that the time period is 0.5 seconds because the frequency is 2 hertz. So now as I decrease the frequency even further, the maximum voltage acquired on the capacitor plates is large, which means it has sufficient time before the pulse switching occurs so that it is asymptotic to its maximum value. The maximum amplitude is 9 volts. Still it hasn't gone all the way up to 9 volts. Alright, so I can decrease the frequency even further. Let me make this 1 hertz. Now it's roughly about 8 and it's still rising. Alright, even though the rise has become less steady and the current has now gone up. You see the current is now roughly 9, the voltage is about 9 volts here. And that 9 volts roughly matches the amplitude that we have over here. I can also increase the frequency back again. And I can actually change the resistor now so that the time constant changes. And how do I change the resistor? By varying this potentiometer. Just a variable resistor. I change it. You can see that the RC time constant is going to change. So now I'm increasing the resistor. So the response is becoming less sluggish. It's becoming more sluggish. And it's now not resembling an exponential because I'm just in the early part of the exponential where it looks like a triangular waveform. So I'm making the resistance large here. So the response is really sluggish. So the maximum voltage built up across the capacitor is really small. It's a small fraction of the amplitude here. So the resistance is really large. So the response of the voltage is sluggish for a capacitor. Okay, I can also, now okay, this connection is slightly flaky. Let me try to reconnect this. Now I'll try to Alright, so now I'm trying to decrease the resistance. And as I decrease the resistance, the response gets sharper. And I can see a large portion of the exponential rise and the exponential decay. Okay? Now look at this. I've gone up to almost the maximum voltage that has been applied. The response is now sharper, so I can see an exponential rise here, just similar to what I have here. And I can see an exponential decay here. This is similar to what I've drawn over here. This is an exponential decay in the current. The current then suddenly switches its direction and then it starts exponentially decaying once again. So during the charging as well as the discharging cycle, the current is exponentially decaying, whereas the voltage exponentially goes up and it exponentially decays. And the time constant is determined by the product of the resistor and the capacitor. So this determines the longer time scale inside this circuit. Alright, so this is what I had to show about this demonstration. Now I move on to something more interesting, and I'll show this the other demonstration in a while. Switch this off. We've also seen in the previous class that the energy inside a capacitor is given by half CV squared. This is the potential energy inside a capacitor. Okay? And it's also given by the total charge on the capacitor divided by 2C. From this we motivated ourselves to the fact that the energy density of an electric field, which means it's the energy stored per unit volume inside an electric field, is really given by 1 over 2 epsilon naught times the magnitude squared of the electric field. And just out of analogy, we proposed that the magnetic field also stores energy, and the energy per unit volume inside a magnetic field is given by 1 over 2 mu naught into B squared. So we would like to convince ourselves of this fact as well. But the key point is that whenever we have electric field, whether it's inside a capacitor or in free space, it stores energy. Whenever we have a magnetic field, it stores energy. It's just like an elastic string. You have a string, you compress or you relax or you extend the string, it stores elastic energy. So an electric field has energy because it requires energy to make an electric field. It requires energy to construct charges on a capacitor. A charged metallic sphere will have potential energy because once it has carried some charge, if you would like to bring in more charge, you have to do work. An external agent has to do work. So in order to synthesize a charged object, you'll have to pump in energy, and that is stored as electric field. Now, with this hindsight, I would like to introduce a second circuit element, because we're talking about circuit elements, and that second element is an inductor. Now let's look at a simple model of an inductor. one inductor that immediately comes to our mind is a solenoid, like the solenoid that I have in front of you here. It's just a coil of wire that is wound around a frame. Inside the frame we have air. So this is my solenoid here. Okay? Just rapid turns of wire on a frame in which we have air. We can insert a magnetic material inside this frame as well. So this is an example of an inductor. Now how is an inductor different from a capacitor, and how does it behave, and how can we come up with a field description of the behavior of an inductor? Now let's look at an inductor. Let's look at this coil of wire. Let me draw a 3D rendering of this wire. I'm just drawing 3 turns of this wire in the interest of time, but these wires, these coils are actually tightly wound together. So now I have a battery. That makes a connection with this coil of wire, which is really a solenoid. And I would like to make this act like an inductor. Now what's going to happen is that these wires, of course, they will have some resistance. An electric field will be set up inside this wire, and that electric field will make a current flow. Now suppose this is a variable voltage source. So this voltage actually goes up with time. Alright? If you have motional EMF, for example, you would notice that the EMF is given by VDL. So if I increase the speed, the EMF goes up. So you can have variable voltage sources in which this voltage is ramped up with time. A simple example of a variable voltage source is an AC source. An AC source provides a voltage, an EMF, which changes with time. It goes up, down, up, down, up, down. Look at the charge across a capacitor. If you're using the charge across a capacitor as an EMF source, the voltage is variable, it's changing with time. So it's not out of this world to have variable voltage sources. So this voltage can go up with time. Now let me look at only one coil, and I'm viewing this coil from here. This is a perspective view of the coil. So I'm viewing the coil from the front, and this is what the turn of wire is going to look like. Now what's going to happen is that a current is going to flow, which actually means an electric field has been set up inside this coil of wire. Alright, so what's the direction of the electric field? It's parallel to the current density. So if the current is flowing in a clockwise fashion, the electric field inside the wire is in this direction. Okay, so this is the field inside the wire. Now where is this electric field actually coming from? Who produces this electric field? Surface charges on this wire. So there is a distribution of surface charges on this wire which produces this field inside the wire. We're all very familiar with these surface charges by now. So there is a gradient of surface charges on this wire which makes an electric field. Okay? The dilution of this charge across this solenoid will be actually gradual. I've only exaggerated this here. So this dilution of charge creates an electric field inside the wire which makes the current flow. Now if the current is flowing in this direction, there's going to be a magnetic field. What's the direction of this magnetic field? Into the plane of the blackboard. Now if this is is a variable voltage source, which really means that this electric field is going to change with time. So this electric field is going to go up with time, which makes the current go up with time. So with time, the field inside the wire is going to go up. Suppose this electric field goes up in this fashion. This is time, this is the magnitude of the field inside the wire. Now when this electric field is going to go up, what's going to happen to the current? The current is going to go up. This is the current through this wire. What is the magnitude of the magnetic field inside this solenoid? The magnitude of this magnetic field is time dependent, and it depends upon the current through this wire, which in turn depends upon the electric field inside the wire. Correct? So if this current is going up, as it's going up here, this magnetic field is going to go up. So the field that is pointing into the plane of the blackboard, it's still going to point in, but it's going to go up in magnitude. And what would that cause? That's a stimulus for a certain effect. What is that effect? Aroma. What's going to happen? If the current goes up, the field goes up, what's going to happen here? Sorry? And magnetic field will decrease. How? Where will that magnetic field come from? In the opposite direction. आप बताओ मुझे जी the current is going up, the magnetic field is going up, so you have a varying flux through this area. What's going to happen in response? Which Maxwell's equations would you like to invoke here? Lenz's law is not a Maxwell's equation. Faraday's law is going to apply here. So you have a changing flux through this region. A changing magnetic flux will produce an electric field of its own. That's going to be a non-conservative electric field. That non-conservative electric field may cause a current through this circuit, and the direction of that current is dictated by Lenz's law, which means that the direction of that current is going to be such that the field that it produces is going to oppose the change in the field due to the increasing current through the solenoid. It's a logical argument. So a non-conservative electric field is going to build up here. That non-conservative electric field, E dotted with dl around this closed loop, is going to be given by minus d by dt of the flux through this area. The flux through this area is Bt into pi r, capital R square, where capital R is this radius. So since the flux is changing, a non-conservative electric field is going to set up. And what's the direction of that non-conservative electric field? That should produce a magnetic field of its own that's pointing outwards, because that opposes the stimulus. So what's the direction of the new electric field that is being set up inside this wire? So it's going to be anti-clockwise. So a new electric field is going to be set up inside this wire, which opposes the original electric field. So this is the non-conservative electric field that's set up. And this has nothing to do with the distribution of charges. Nothing is moving here. It's not motional EMF. It's only a time-varying magnetic field due to a time-varying current. So this non-conservative electric field is pointing now in the opposite direction, which means that the net field inside this wire is going to diminish. It's going to decrease. So now if I make a plot of this, a diagram of this piece of wire again, in this region when the current is increasing with time, the net field inside this wire, which was originally pointing anti-clockwise and it was large, might diminish a little bit. So this is the new field, the net field that is set up. it might still point in the clockwise direction because the non-conservative electric field may not be large enough to completely counteract this field. So this is a net field that's set up. This net field is the original field E wire, which by the way depends upon time, plus the non-conservative electric field inside this wire, which also depends upon time. This comes from charges, this doesn't come from charges. This comes from changing magnetic fluxes and from Faraday's law. So the electric field inside diminishes. Now if I would like to model this behavior, I have a battery that is connected to this solenoid. This is my solenoid. This is, suppose I also have some resistor here. All the wires' resistance can be lumped into this resistor, or I can have a nominal resistor, a real resistor. Now what's going to happen is that effectively an electric field is going to be set up inside this wire, which is going to oppose the battery. So this object is really being modeled as another voltage source whose voltage distribution is like this. It's acting like a battery. So in the back of my mind, I can think this model as being totally equivalent to a real battery and another battery which has an induced EMF, an EMF that is induced. Of course this is an induced EMF, and then a resistor. Now the polarity of this induced EMF is such that it opposes the polarity of the real battery, of the voltaic cell. So the voltage across this solenoid acts like an EMF source. And the voltage across this solenoid, we can find out what that voltage is. That voltage would simply be given by this. This is an EMF. Remember, it's an induced EMF. So the magnitude of this EMF, of this inductor, is going to be given by its magnitude. We are only interested in magnitudes here. We know what the polarity is. The polarity is given by your Lenz's law. This is given by pi r squared into d by dt of the changing magnetic field, which is mu naught n I t. Now mu naught n is a constant, so I have pi r squared mu naught n di by dt, the rate of change of current. If this voltage drops with time, which means that I'm in this regime of the electric field, that is, I have an AC voltage and the voltage drops, then this EMF switches its direction. But at the same time, this EMF is going to switch its direction, just by Faraday's law. It's going to switch its direction so that this battery, the induced EMF, is always going to oppose this EMF here. It's always in the opposite direction. So when this happens, this is the magnitude of the induced EMF. It doesn't matter whether the current is going up or down, whether this is positive or negative, there is an induced EMF, and it's always going to oppose the original battery. Now if you look at this expression, what do we have? We have something quite interesting here. We have an induced EMF that is proportional to some constant into the time rate, the change of the current through this EMF. This object is called the inductance of this solenoid, and it's represented by L. So the induced EMF inside a solenoid or any inductor, a solenoid is just one special kind of what is called an inductor. This is equal to L di by dt. The current through a capacitor I is given by dq by dt. This is through a capacitor, but Q is given by C dV by dt. This is a current through a capacitor, This is the voltage across the capacitor. This is the potential drop across an inductor. The potential drop across an inductor is given by the inductance of that inductor multiplied by the time rate of change of the current. The current through a capacitor is given by the capacitance multiplied by the rate of change of voltage across the capacitor. So inductors and capacitors are two major elements, circuit elements, that stand hand in hand. They stand together, and both of their properties can be described in light of Maxwell's equations, in light of fields. Faraday's law here, Gauss's law here. Gauss's law and Ampere Maxwell displacement current. Now if you look at this induced EMF and if you look at this circuit here, you can actually construct a differential equation that tells you what the current through this circuit is going to be. So look at this circuit here. This induced EMF is given by L di by dt. Now around this closed path, what's going to be the line integral of the electric field? That's going to be 0. If a current is flowing through this circuit, E dot dl around this path has to be 0. So Kirchhoff's voltage law is going to be applicable here. So if you apply Kirchhoff's voltage law here, E, the EMF of the battery, I'm going to mathematize what happens inside an inductive circuit. Further, so E minus E induced minus IR equals 0. You go around this circuit, alright, let me draw the circuit again. You have an inductor, L, and a resistor. This is the EMF. You go around this circuit in this path, the voltage increases. It goes from minus to positive, then it goes from positive to negative, so it drops. Here it goes from positive to negative, so it drops. This current is actually flowing because of a charge gradient, which means that E dot dl has to be 0 across this path. And that's why Kirchhoff's voltage law is applicable. Alright? So if we look at this circuit, we would like to write a differential equation for this. This is what the differential equation is going to look like. Now, but this E induced is L di by dt minus IR equals 0. Now I'm going to just shuffle this equation a little bit. Di by dt plus R over L Madani. This equals the EMF of the battery divided by L. Now this is another differential equation. It's very similar to the differential equation we constructed for a capacitor, isn't it? The differential equation that we constructed for a capacitor was very similar to what we have here. Now if I solve this equation, the current through this circuit is going to be, can you solve this differential equation? Please, can you do that for me? क्या हो? Alright, sorry. So this is what we get when we solve this equation. At time t equals 0, this is 0. There is no current through this circuit. Which means that the inductor is opposing any change in the current. Correct? When time is really large, this term goes to 0, so the current then freely flows through the circuit as if the inductor were not present. So the EMF, the current is simply given by the EMF divided by the resistor. So the inductor is opposing any changes in the current. If I look at the charge on a capacitor, that charge on the capacitor is given by Q naught, some maximum charge say, which, alright, into 1 minus E minus T over RC. And if I look at the voltage across a capacitor, that's simply going to be the maximum voltage across the capacitor, which is the EMF of the battery, 1 minus E minus T over RC. So compare this response of a capacitor to this response of an inductor. This is for a capacitor. For a capacitor, what we observe is the following. Time, the voltage across a capacitor, it changes like this. Initially, the voltage across the capacitor is 0, but the capacitor cannot suddenly pick up voltage. The voltage is gradually building up inside a capacitor. So the voltage response of a capacitor is sluggish. It opposes changes in voltages, in other words. It doesn't want its voltage to increase instantaneously. There are no rapid changes in voltage across a capacitor. It's like a voltage opposer. The voltage is trying to pull it up to a certain level, but the capacitor is lagging behind in its response. An inductor, on the other hand, if I plot the current through an inductor, IL, that's why I put in a small L here. Its response in the current is sluggish. So it does not like to change its current, because changes in current will produce an induced EMF which opposes the change in the current. The voltage built up on a capacitor opposes the EMF of the battery, because then the voltage across the capacitor is pointing in the opposite direction to the EMF of the battery. So a capacitor has a slow voltage response, whereas an inductor has a slow current response. Likewise, if you have the same circuit here, and then you have an inductor, and then you have a resistor, or an L. So an EMF has been developed across this inductor, alright, or it hasn't been developed, and there's a switch here. This switch was initially closed. Alright. Now what we would like to do is we would like to open the switch rapidly. So what we have here is a voltage across the inductor. That voltage across this inductor is acting like a source. Now what's going to happen is that if this switch opens up rapidly, there's some current flowing through this circuit. Okay, so we intercept this circuit somewhere at time t naught. There is some current flowing through the circuit, I at time t naught. Then what we would like to do, so there was current flowing here, to open a switch here. So this battery is disconnected, but at the same time you open another switch. So the current through this inductor is going to rapidly go down to 0. So there was a current flowing through the inductor. Now you would like the current to rapidly go down to 0. Current cannot flow because the switch is open, the circuit is not closed. That will create a large voltage change in this inductor, because the induced EMF is given by L di by dt. If the current rapidly goes to zero at this point, just because you've opened up the switch here, what's going to happen? A large EMF is going to be introduced. Now this large EMF that is going to be introduced will make this end of the switch positively charged and this end of the switch negatively charged, because current cannot flow actually. So this is a conductor, so all of this positive charge is collected here and all of this negative charge is collected here, and there's not a dilution of charge, but the charge is evenly spread out in this conductor because the current is not flowing, the switch is open. So this terminal of the switch becomes negatively charged, this terminal of the switch becomes positively charged because you suddenly drop the current to zero. This large voltage difference that is built up because this is really large, the current has gone down to zero in a very rapid instance of time. di by dt is really large, this EMF is really large. It's just like having a large voltage source, possibly kilovolts, in across this switch. That might cause sparking across the switch. So rapid dismissals of current or rapid arrests of current might cause large voltages to develop up because of this behavior of the inductor. It produces a large EMF which is proportional to di by dt. This might cause sparking across the switch. And if there is some volatile gas, it might cause an explosion as well. This is how an induction coil works inside an automobile. It produces a spark. So this coil is called an induction coil inside an automobile. Alright? So this is what I wanted to discuss about inductors. But let's look at the inductance of this coil. So for a solenoid, we can find out what the inductance is. That inductance is simply given by the cross-sectional area pi r squared into mu naught n. N is simply the number of turns per unit length. Let's call it small d. So this is the inductance of a solenoid. The self-inductance of a solenoid. A current flows through this solenoid, the current is changing, it creates a voltage that opposes the change in the current. And the amount of voltage it creates is proportional to the inductance of this solenoid. Alright? You wind it tighter, N over D is large, so the inductance is large, the induced EMF is large. If you replace mu naught, if you put inside this solenoid a piece of iron, which has a permeability mu instead of mu naught, the inductance goes up. That's why in transformers you don't want to use air, you would like to put in another material which has a different mu, not mu naught. Now in the last 15 minutes, I would like to come up. By the way, you can also calculate the inductance of a toroid, for example. If I have a toroid here, and there is a wire that is wound around the frame of this toroid, now the field is inside the toroid like this. Now if the current that goes in is changing with time, this current is changing with time because I have an AC source, for example, or a variable voltage source, then the induced EMF inside this toroid is going to be given by, now the EMF is just given by Faraday's law here. This is ENC dot dl. Around this closed path, ENC dotted with dl will be given by, its magnitude is the time rate of change of the field. Now what's the field? The field is Vt. And what's the area? What area are we going to talk about here? What area should we take? Exactly, it's the cross-sectional area of this toroid, nothing else. Not the area inside here, because the field is penetrating inside this area only. So I take Vt into the cross-sectional area of this toroid. Remember, you have to choose your areas properly. I'm noticing that you don't choose your areas properly. Here the area is not the cross-sectional area of this donut, it's the area inside this frame, because that's where the magnetic field is. So this is the induced, but the magnetic field, we've already calculated the magnetic field inside the toroid. that is mu naught capital N IT divided by 2 pi R. Now this is the R that you need to take. Okay? This is the magnetic field and this is capital A. So this capital A is not this pi R squared, remember. This is the cross-sectional area of the toroid. And the time derivative of this, of course. Now if I look at this, the inductance of a toroid, if I just remove the di by dt, whatever remains is the inductance of the toroid, mu naught N A over 2 pi R. In this way, I can calculate the inductance of any geometry that I like. A solenoid and a toroid is actually quite a simple example. Remember, for a capacitance, the capacitance also depends upon the geometry. So the inductance and the capacitance are geometrical parameters. They are determined from the geometry of this system. And what material has gone into the construction of these devices. The material is put in this constant. If I have a dielectric, which I describe in the next class, I put in a constant called the relative permittivity. If I have a magnetic material, I put in the relative permeability here, mu R, which is just 1 plus chi m, where chi m is the magnetic susceptibility. Ferromagnets have large chi m, so they have large mu R, they have large inductances. Now what I would like to talk about is the concept that we've seen so far is that of self-inductance. Now I would like to talk about in the last 10 minutes of mutual inductance. देखो कोई रफ्तार ज़्यादा तेज तो तेज है देखिए आपकी मैच्योरिटी लेवल भी बढ़ता जा रहा है इसलिए रफ्तार भी तेज होगी अब आप यूनिवर्सिटी में मैं भी यूनिवर्सिटी में उस्ताद इसलिए तेज चलता So a teacher inside the classroom has to just expose the surface of a landscape. It doesn't dig really deep. It's for you to go deeper. Now I would like to talk about mutual inductance. Now quite an interesting demonstration I built for you. And that will bring home the concept of mutual inductance. So in mutual inductance what we have, suppose I have a solenoid. And this is connected to an AC source. So the current to this solenoid is varying. Let's call this current I1. This current will depend upon the magnitude of this voltage, the resistance of this circuit. It's a long piece of wire, so it will have resistance, and the inductance. Alright? Now this will produce a magnetic field. If the current is flowing in this direction, so it's flowing around like this, what's the direction of the magnetic field? It's going to point downwards. But when the current goes up, it's going to point upwards. So there is some axial magnetic field that is changing its direction. If I plot the magnetic field versus time inside this solenoid, let's call it B1T, that field is going to change sinusoidally. And it's going to point in general axial direction. Sometimes it's pointing up, sometimes it's pointing down. Because this current is sometimes clockwise, sometimes it's anti-clockwise. Now what I would like to do, so an EMF will be induced inside this solenoid. That EMF, let's call it EMF 1, is given by the inductance of this solenoid L1 into di by dt, di1 by dt. This inductance will be given by the formula that we just derived. So a voltage will be set up inside this inductor. Now what I have is another solenoid that is wrapped around this solenoid. And there is no voltage source connected to it. Rather, I have a voltmeter, for example. Now what's going to happen is an EMF will be induced in this second solenoid that is not connected to a battery because of induction. That EMF in the second battery is going to be given by Faraday's law. Its magnitude is going to be equal to the time rate of change of the flux through the blue solenoid, to the area of the blue solenoid. Alright? So that flux is going to be equal to, let's call it phi 2t. That phi 2t is going to be given by the number of turns of the second solenoid, N2. This has N2 turns into the field into the area. Now what field are we talking about? The field is given by V1t. So the time rate of change of V1t. And what area are we talking about? It's the cross-sectional area of the second solenoid. But the field is only inside a small region of the second solenoid. So if I look at the top view, this is my blue solenoid. This is one coil of the blue solenoid. This is one coil of the inner solenoid, the primary solenoid, and the field is only existent inside the inner solenoid because it's a tightly wound solenoid. There is no field outside. So the magnitude of that field is B1. It's produced by the current in the primary coil, but the area that we're talking about is only this area, because the field here is 0. Only inside this area is the field non-zero. So I have to take the area of the inner solenoid. Okay, that area is, say, A1. Do you all get this point? Even though I'm taking the flux through the blue solenoid to an area which is spanned by the blue solenoid, there is no field in here. So I'm effectively only reduced to taking the area inside the primary solenoid because only the field exists inside that area. Had the field existed here, I would have taken into account this area as well. Do you get my point here? So this is the EMF induced inside the primary, inside the secondary or the outer solenoid. Okay, even though no battery is connected to it. Now if I look at this EMF, this is N2. This area A1 is constant. d by dt of B1t is mu naught small n1, which is the number of turns per unit length of the inner coil. Small n1 into the time rate of change of the current through the primary, di1 by dt. Now what we observe here, an EMF is induced inside the second solenoid by a changing current through the first solenoid. The changing current through the first solenoid induces an EMF in the second solenoid, and there is no electrical contact between the first solenoid and the second solenoid. This is the concept of mutual induction. And this object here is called capital M. It represents the mutual inductance of this circuit, of the two coils. And it depends upon the number of turns of the second solenoid, but it also depends on the number of turns per unit length of the first solenoid and the area of the first solenoid. So an EMF will be induced in the second solenoid. Now what I have here in front of you is quite a nice demonstration. Let me first describe what I have in front of you here. I hope it works. It takes quite a bit of time to develop these. Thoda sa zoom out karo. Alright. So look here. have a function generator. This function generator here produces an AC voltage. That AC voltage is amplified by an amplifier. That amplifier is powered up by a battery, nevertheless, but this amplified voltage from the primary current goes into a solenoid. This is my first solenoid. Now what I would like to do, I would like to take a piece of wire, wrap it around the first solenoid. The piece of wire will act as a secondary coil. And an EMF is expected to develop around that secondary coil. A mutual EMF, a mutually induced EMF. That EMF is really small because this is air inside and the fields are really small. So I'm going to amplify that voltage by another amplifier. And I'm going to filter it a little bit. I'm going to signal condition it so that the waveform looks nice, and then I'm going to display this on an oscilloscope. Okay, I hope you understand the scheme of things here. You get it? Alright. So I'm going to turn on things for you. So I turn on, first of all, I would like to turn on my amplifier, my audio amplifier for the primary current, which means I connect it to the battery. So this amplifier is now on. I turn on the function generator here. So it's producing a signal of 1.29 kilohertz. That's why I'm using an audio amplifier here, because I'm working in the kilohertz regime. This amplifier is on, and this is my oscilloscope. Can you please zoom in on the oscilloscope a little bit, just a little bit, Ali? Alright. So I have a sine wave. A sine wave is going into the solenoid. Now I have another piece of wire here. I have another piece of wire here. And the EMF across this wire, oscilloscope, this EMF is 0 here, so that's represented by the blue line here. There's no EMF. It's just wrapped, it's just dangling in air. There's no changing flux to this. Now I'm going to wrap this around this solenoid gradually, and I expect that a voltage will be developed inside this piece of wire. Okay, I'm going to wrap it. Great. Already you can see an EMF has been developed across this. I make one wrap. Okay, एक फेरा, दूसरा फेरा. The voltage is going up. It's already gone up because the number of turns in the secondary coil has gone up. Now I make another round. The voltage goes up even further. Okay, let me try to amplify this effect a little bit by increasing this. Okay, now I'm going to do one wrap. The voltage goes up. Alright, one wrap, the voltage has gone up. Second wrap, the voltage goes even further up. Third wrap, the voltage goes even further up. I'm increasing N2, capital N2, the number of turns in the secondary coil. The voltage is going up. A fourth wrap, the voltage has gone further up. Okay? Nothing has happened to the primary current. The yellow waveform is unchanged. Just by increasing the number of wraps, I can increase the induced EMF. Now what I would like to do, I would like to unwrap. I unwrap this wire, the voltage goes down. I unwrap, the voltage goes down. Unwrap again, the voltage has gone down further. I move this wire out of this circuit, the voltage has gone 0. So the EMF does, the electric field which is causing a current through this piece of wire does depend upon the path. The electric field is path dependent, because here we're talking about a non-conservative electric field. The electric field does depend upon path. The voltage does depend upon path. Now let me do something interesting. I make one wrap. Now I'm doing a wrap in the clockwise direction when seen from above. The second wrap is also in the clockwise direction when seen from above. The third wrap is also in the clockwise direction when seen from above. Now I'm doing the fourth wrap, but in the anti-clockwise direction. E dot dl. I'm going to change E dot dl. Or I'm going to change the right hand side of the Faraday's law. It depends upon how you look at it. Because the area has now changed its direction. Now I'm going to do a fourth wrap, but in the opposite sense. Let's see what's going to happen. The voltage has gone down. So even though I'm doing a wrap, but I'm doing a wrap in the opposite sense, which means that the direction of the area is changing, but the field is still in the same direction. So B dotted with D is changing its sign. So the EMF changes its sign. So now I have 2 or 3 batteries in one sense, and the fourth battery, because of the fourth wrap, is in the opposite sense. Quite a vivid demonstration that the electric field depends upon the sense of wrapping as well. I do another wrap in the opposite sense, the voltage goes down further. So now I have 3 wraps in one sense and 2 wraps in the opposite sense. Those opposite sense wraps produce conservative or non-conservative electric fields in the opposite sense, or they create induced EMFs in the opposite sense. This is a beautiful demonstration of Faraday's law about what direction does the area vector point in. Now I'm going to do something. I'm going to make this. I'm going to make a coil here. This is just a coil here, piece of coil. But now I'm going to insert this piece of coil inside the solenoid vertically, so that no flux pierces through this solenoid, through this secondary coil. So I'm changing the orientation of the area vector. So a small EMF may be developed because I'm not perfectly vertical, but let's see what's happening if I just plumb this into the solenoid. A really small EMF is going to be developed because now my area vector is not pointing in the right direction. It's not parallel or axial with the solenoid, hence it's not parallel to the field. The last thing I would like to demonstrate, I'm going to wrap this around this solenoid once again. Oops. Yeah, Ali? And you notice one interesting fact here. इस पे zoom in करो please. The primary current or the primary voltage and the secondary voltage are not in phase. So if one of them is sine omega t, the other is the derivative of sine omega t, which is cosine omega t. Hence the two voltages are 90 degrees out of phase. If one is a sine, the other is a cosine. Therefore the primary and the secondary voltages or the induced EMFs, they're not in phase with the inducing voltage. There's a phase difference because of the derivative of the current. If one is sine, the other is cosine. So one waveform is 90 degrees out of phase with the other. Last thing, let me try this. If I increase the frequency a little bit, what's going to happen is nothing is going to happen to the primary, to the yellow, but the induced EMF is going to go up. The induced EMF is going to go up because di by dt is going up. The frequency increases. If I is sine omega t, its derivative is I omega into cosine omega t. So dependence upon the frequency is also pronounced. You increase the frequency, the induced EMF also goes up. I'm now increasing the frequency, it's 2 kilohertz. The frequency is going further up, up, up. So I just move these blue lines downwards. So this frequency is now increasing, it's about 3 kilohertz. The induced EMF is going up, and now I'm at the range of 5 kilohertz. I've just increased this to 52 kilohertz, but now I'm outside the range of the amplifier. Alright, so the induced EMF also has a strong dependence upon the frequency. Thank you very much. See you on Thursday. I'm going to talk about dielectrics,